Hello again. Um, I'm looking forward to hearing about the applications you came up with. But here's another one that I was thinking about. Say we're at the National Park Service and want to group a bunch of campgrounds represented by the blue circles on the map into different clusters based on their location. Maybe we want to recommend related campsites for campers who are unable to get into a camp when it fills up. So if these are the campgrounds represented by these big blue dots, then the only things that are relevant for grouping based on location are their latitudes and longitudes. So we don't really need the map. We can just put them in this location space. We'd ideally like some number of clusters like this. This looks fairly reasonable if we're allowed as many clusters as we need. But of course, there are other ways to group them as well. And looking back at the map, doing this kind of clustering would give us about 7 clusters of campgrounds, which could be useful to describe distinct camping regions and maybe organize the website for people to make camping reservations. So there are a few things that are useful to say about this example. So the first is that some algorithms to do this will allow flexibility. So basically discover from the data how many clusters you need, whereas others will require you to specify at the beginning, before you run the algorithm, exactly how many you're going to use. And of course, the features here mattered again. So this is one thing that I'm really trying to drive home, is that we specifically were looking at clusters in terms of geographic location, and these latitude and longitude features, but there are many other things that might be important for thinking about similarity of different campsites. For example, elevation, if you're interested in grouping campsites in different kinds of terrain, maybe alpine campsites versus wooded campsites, or things like the size of the campsite, the cost of spending a night there, and so on. So you could examine the kinds of clusters you get for each of these kinds of features. So there are a lot of algorithms to implement clustering and get clustering like the one that we saw with these campsites. But one of the most widely used is called k-means clustering. So this is where we'll begin. So this algorithm is a kind that requires you to specify upfront exactly how many clusters you want. That's the K in k-means clustering. So you say, we want to group our data into 5 clusters. Now, this is a parameter. You can rerun it with different choices of K to see different things you get, but the algorithm depends on a particular K being chosen. This algorithm proceeds from a very simple principle, which is to measure similarity in some kind of geometric space. So you need to be able to embed your examples in some feature space where you can measure distances. And then finally, this algorithm requires every single example to belong to exactly one of the K clusters. So at the end, you'll get an assignment of every data point to exactly one cluster. So this doesn't allow overlapping clusters, allowing a single data point to belong to multiple communities, for example. And it doesn't allow any outliers to exist outside of one of these clusters. Okay, so the algorithm works like this. You start by randomly picking points in the space. So these are called centroids. So we'll proceed through this graphically in a moment, but I just want to give you a preview of what this looks like. So you essentially pick one centroid per cluster, and you're going to proceed in the algorithm by kind of alternating back and forth between two steps. So the first thing you're going to do is take every example around that cluster and assign each example to the nearest centroid. And then now you have a bunch of points that have been assigned to that centroid, and then you can move the centroid to the middle of the examples that were assigned to it and repeat. So this sounds a little complicated, but I think it helps to look in an example. So here's some data that was synthetically generated to have exactly 5 clusters in this 2-dimensional space. And we want to recover what these clusters are. So let's follow this algorithm. So step 1 is we're going to pick 5 points. Here, these points are represented by stars. You can try to eyeball and squint to see where all these stars are. You see that there's a dark one in the bottom left, center left cluster. There's one right above it. There's sort of 2 stars next to each other in the top cluster, and one initialized in the bottom right cluster. So these centroids are just not actually data points, okay? They're things that we as the experimenter create and initialize in our code. So we say, generate 5 random points in this space. Okay. Now, because this is a 2-dimensional space where every point belongs to some x coordinate and y coordinate, we can measure distances from every point to every other centroid. So for example, we can take one of the points in this top part of the screen and measure the Euclidean distance to that green star, to the blue star next to it, to the orange star in the bottom right corner, and to the green and black stars on the left side. And then for that point, we color it according to the closest centroid, okay? So in this case, the closest one was green. Now, we do that for every single example as shown. So every single example in our data set, all 1,000 points represented in this graph, now have a color based on the nearest centroid dot. Okay, so another way of seeing this very clearly is for the 2 stars that are very close to one another in that upper cluster with green and blue, you see that the points halfway between them create this very clean line where the points on the right-hand side go to blue and the points on the left-hand side go to green. So this is the step 2. Now, we alternate to a different step where we recompute the centroids. So now we fix the colors of the points and figure out the place that is the average center location from all of those points. So that's going to move a little bit. And again, the clearest way to see this is with that blue star on the right-hand side. So as you can see here, all of these dots in that far upper right cluster got assigned to blue, even though the blue isn't super near them, just because it was closer than orange, okay? So then when we recompute the centroids, blue now moves to be halfway between all of those blue dots on the right-hand side that got assigned to blue and the ones that were previously close to the star. So we're now shifting the centroids around, and then we're going to repeat. So we're going to now fix the centroids and measure the distance of every example to the centroids and color them, and then move the centroids again with the examples fixed. So basically we're alternating between fixing these stars and coloring the dots, and then fixing the color of the dots and moving the stars. So over enough time of repeating this process, the centroids move. So at least in this particular example, we're now continuing to repeat and noticing that these stars aren't moving much anymore. So this is considered convergence, and this is a good sign. So it means that we've kind of settled into a set of clusters, and the algorithm is complete. So we can cover the details of this in further detail in the live TA hours later, and you'll be playing with this a little bit as well in a Jupyter notebook. So you can see for different kinds of data, the kinds of clusters that come out of this process. But the point of this alternation is that we can basically coax our centroids into the place where they can cover the most similar dots as possible. So over time, the centroids will get pulled into the places of highest concentration of dots in this space. Now, how can we tell if this clustering is good? So we've run this algorithm, it converged, it gave us an answer. And it would be nice if we could have some sort of accuracy metric. So when we were doing classification, there's this very nice idea of a test set where we could just look at error on the test set and say that you know, if we achieve higher accuracy on these held out examples, we've learned something better. But what is the analog of that for unsupervised learning? Well, this continues to be an interesting area of study to evaluate the goodness of unsupervised metrics. But there are several ways that can essentially look at how well it captures the overall similarity within and across clusters. So we won't cover these in detail, but there are various metrics that have been proposed that allow you to see how well you've been able to kind of partition the space of examples into coherent clusters versus what you would expect, you know, if you just took a random grid of points and assigned them to 3 clusters. Those the underlying data aren't that structured, so your clusters aren't going to be so super cohesive. Okay, so these are basically various mathematical formalizations that that you can look into on your own, or that you're welcome to ask instructors more about if you're curious. Okay, so I think another takeaway besides this sort of mechanism of the k-means algorithm is this idea of what to do with these features. So it really required having this space where you could compute distances. And unfortunately, as with supervised learning, feature selection, picking exactly what that space ought to be, is one of the most important parts of running an unsupervised learning algorithm. So for instance, we may want certain features to be weighted more heavily than others. We may need to scale some features that are on different scales than others so that they don't dominate distances. So you can imagine that, you know, if you have one dimension that's stretched out really far and another dimension that's smooshed together into a very small interval, you might want to standardize those by by normalizing your data first to get everything on the same scale.